Welcome back to Series on Catalyst University. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. Alright, so in the previous video, we actually covered the theory behind the integral test for series, and we did an example where we saw that the integral diverged, and so the original series also therefore diverges. We're going to do another example here. So if you need more help with these integral tests, go back and watch the previous video. I'm going to assume here that you understand when to use the integral test. We're just going to go for it. Here's my original series up here. I've got the series from n equals 2 to infinity of 1 divided by 2n plus 7 cubed. All right? So remember, what I need to do is pick my a sub n, which is basically just the argument of this series. Okay? So a sub n is 1 over 2n plus 7 to the third power. Now, for the purpose of integration, which is eventually what I'm going to do, remember I can also rewrite this as 2n plus 7 to the negative third power. Okay? Now, I need to show, first of all, before I do any integration, that this a sub n is both positive and decreasing. Well, if I want to show it's positive, I can just plug in a number in this series into the n. Well, 2 is included in this series. Let's just use 2. So it'd be 2 times 2, which is 4, plus 7 is 11. So it'd be 1 over 11 cubed, which is positive. And if you think about it, no matter what number I plug in for n here that's included in this series, which are all positive numbers, it's never going to be a negative number. It can be a really small number, but it'll never be negative. So this is definitely a positive function. Other thing I need to prove is that it's decreasing. And really all I need to do with that is just plug in a few numbers. If I plug in 2, like I said, we have 2 times 2 is 4, plus 7 is 11, so 1 over 11 cubed. If I plug in 3, it becomes 3 times 2 is 6, plus 7 is 13, so 1 over 13 cubed. And then you would go 1 over 15 cubed, 1 over 17 cubed, and you can see that it's decreasing for the entire function. Now remember what I said. It doesn't have to be decreasing for the whole function. It can be increasing at first and then decreases for the remainder of it. But the point is, it just has to be decreasing at some point and then to the end. Okay? It has to be decreasing as it goes to infinity. Okay? This one's decreasing the whole way. So these two conditions are satisfied. Now we can actually run the integral test. And this one will require a u substitution. My integral, by changing all the n's to x's, is the integral from 2 to infinity of 2x plus 7 to the minus third power dx. Now, I'm going to have to use a limit again because I really, by the technical rules of improper integrals, I can't do the infinity explicitly. So it's the limit as t goes to infinity of the integral of 2 to t of 2x plus 7 to the minus third power dx. All right, now what I'm going to do is this 2x plus 7, if you want me to be really explicit, I'm going to do a u substitution. So u equals 2x plus 7. I can then say du is equal to 2 dx. All right, and to get it in terms of only dx, I can divide both sides here by 2, and I get 1/2 du is equal to dx. And because I've got a dx right here, I can replace that with a 1/2 du. So that's what I have down here. Here's my du. I've gone ahead and plugged in for 2x plus 7, the u here, still to the minus third power, and then this 1/2 I just pulled out in front of the limit. All right? So it's now 1/2 times the limit as t goes to infinity of, now we're really not in x units anymore, so I'm just specifying that these bounds are from x equal to 2 and x equal to t of u to the minus third power du. Let's just do the integral. So we raise the power by 1 and divide by that power. So it becomes the limit as t goes to infinity of 1/2 times u to the minus half, or u to the minus 2, excuse me, over minus 2. All right, again, we're going to be evaluating from x equals 2 to x equals t. I sort of forgot those here, but you get the point. It'd be the limit as t goes to infinity. Now I'm going to pull the negative sign up on top, and 2 times 2 is 4. So it's negative 1 over 4 u squared, because this is u to the minus 2 in the numerator, so pulling it into the denominator becomes u squared down here, and it's from x equals 2 to x equals t. Now, I'm going to back substitute. I'm going to now take this u and return it to terms of x. So it's the limit as t goes to infinity of minus 1/4 times 1 over. Now putting this expression for u back in, 2x plus 7 to the second power, evaluated from 2 to t. All right? Again, the only reason I pull this 1/2 in here is so you could see 2 times negative 2. Now I'm going to pull this negative 1/4 out, and so I have negative 1/4 times the limit of t goes to infinity of 1 over 2x plus 7 squared from 2 to t. All right? That's what I had up here. I just pulled the 1/4 out in front with the minus sign. So now I'm going to evaluate this. Let's first evaluate it at the upper limit, t. Negative 1/4 times all of this. The limit as t goes to infinity of 1 over 2t plus 7 squared. Now let's plug in the lower limit, which we don't need the limit for. So minus, that's a 2, 1 over 2 times 2 plus 7 quantity squared. All right, now let's first worry about this second part over here, which is a lot easier to evaluate. So I've got 2 times 2, which is 4, plus 7 is 11. So it becomes 1 over 11 squared, right, with a minus sign, of course. That's easier to do. But now, what happens if I plug in infinity for t? If I let this first term go to infinity, at least the t, it becomes just 1 over infinity. Because 2 times infinity plus 7 is still infinity, squared is still infinity. So 1 over infinity is 0. So if I multiply all this out, and it's, you might need a calculator if you're not perfect with this. The negative signs cancel, right? 1 over 11 squared is 1 over 121. And then times 1/4 is our final result, 1 over 484. All right, let me ask you a question. We did this integral and we got 1 over 484. Does that mean that this series, the original series, equals 1 over 484? No. All the integral test tells us is if the integral converges, which it did, it converged to this value, then the original series converges. Okay? Remember, it doesn't tell you the value, it's just that whatever the integral does, the series does. So like in the previous video, because this integral diverged, the series also diverged. So in this example that we just did, because the integral converged, this series also converges. And so this series up here would be a useful series to use for whatever purpose, okay? Because that's what these tests are telling us. We want them to converge, all right? So this series converges, okay? And that's pretty much all there is to it. And that's a lot easier said than done. The easy part is showing it's positive and decreasing. The bulk of this problem is really actually computing the integral, okay? And then saying it converges or diverges. All right, thank you for watching this video. Hopefully you learned something. Please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you very much.